In section 7.4 and 7.5, we're going to shift gears a little bit. We're going to use some of the stuff we talked about in the first two sections in this chapter, but in 7.4 and 7.5, we're going to focus on vectors. So you see in your notes a definition of a vector. Vector quantities are quantities having both magnitude and direction. So there's a magnitude, there's a number associated with it, and a direction. And a vector is a directed line segment. So we represent a vector with a magnitude and direction as a directed line segment. So a line segment, well, you know what a line segment is. It's just a line segment. Now, it says it's a directed line segment. So there's a direction associated with this line segment, and we indicate the direction with an arrow. So we put the arrow at the end like this, but when we did ray, remember, the arrow at the end meant kept going, right? Whenever you did a ray in high school geometry, that's what the arrow at the end meant. This is a line segment, so it actually stops. The arrow just tells you you started here and went to here. That's all the arrow means. Okay, so you have to get it from context. Is this a vector or is it a ray? Okay, so we call this where the vector starts. That's the initial point. And where it stops is called the terminal point. Now, where we've seen those vocabulary words before, remember those were the same words we used with an angle, the initial side, and it rotated to the terminal side. So we start at the initial point and we stop at the terminal point. So if I call this point, say, A, and I call this point here B, you can write this as AB with a little arrow above it. Now, this means start at A and go to B and stop. Now, that was the same notation we used for array. But again, you have to take it from context. But AB is not the same as BA. Okay. Now, we're writing vectors in the book and in the typed notes with boldface. So typically, you know, vector U, they'll write as boldface. So I can't do that on the board. It's annoying. So in the notes and in the book, they're written in boldface. But on the board, I will just write U with a hat on it to indicate it's a vector. So that's how you know. So in the notes, it's a boldface U. On the board, I'm going to put the little hat on it. Okay, so that's what a vector is. So vector is a directed line segment. It's that thing I just drew. So the length of the segment of the vector is called the magnitude. And we denote the magnitude with vertical bars. So what I had just there a second ago, you could say, right, this. Now, you don't read that as absolute value. It's the same notation, but we're using vertical bars just like we did for absolute value. How do you know this is not absolute value? Because what do you take the absolute value of? You take the absolute value of a number, right? And this is not a number, it's a vector, okay? So this is the magnitude of the vector. It's just the length. Okay, that's all that means is length. Vectors with the same magnitude and direction are called equal vectors. Whenever you learn a new concept in math, you want to know what does it mean for two of them to be the same thing. Well, I'm going to draw two pictures here. So suppose I drew this. There's vector U. And suppose I drew this, and I called that vector W. And I tried to make them have the same length. So the length of U, the magnitude of U, is equal to the magnitude of W. Okay, so if they have the same length, the magnitudes are the same, but vector U is not the same as vector W. Do you understand the difference? These are just saying the lengths are the same, but they're not the same vector, because what does it mean for two vectors to be the same thing? They have the same magnitude and same direction. This one's heading in a northeast direction, this one's heading in a southeast direction. So they have the same magnitude, but they don't have the same direction, so they're not the same vector. Okay, now what's a picture of two vectors that are the same? Let me draw vector V here. Now compare vector V to vector U. I tried to draw them with the same length, and notice they're both going in a northeast direction. So vector U and vector V are actually the same vector. Now obviously the lengths are the same. If two vectors are equal, their magnitudes are the same. But just because magnitudes are the same does not mean they're the same vector. And when we say same direction, what we mean by the compass, that doesn't mean they start at the same place and stop at the same place. Okay? Northeast, northeast. Okay, so how could you represent a car going 30 miles per hour in a southeast direction with a vector. Okay, well, so imagine the car is starting here, say, and it's going in a southeast direction at 30 miles per hour. Okay, so if I draw a vector like this, that indicates the car is going in a southeast direction. And if I call this vector u, and I say the magnitude of u is 30, okay, there you go. So that's the way you could do that. Now what's the problem here? I mean, having one vector doesn't really, I said the length is 30, but what do you really want vectors like this, pictures, so you can easily compare two of them, right? Having one, you'd have to say, well, that's 30. You have to tell the person, right? Then it says, how can you represent a car going 15 miles per hour in a northwest direction? Okay, now I'm still using this as a guiding example. So I want a car going in a northwest direction, so this way, but 15 miles per hour. Well, the magnitude, the length of this vector, we say 30. Now be careful here. Notice 30 here is referring to the miles per hour, which is not a length, it's a rate. But you could, this isn't 30 centimeters, but you could say, if this is 30 centimeters long, that represents 30 miles per hour. So the length of the vector may represent a quantity whose units are not length. Okay, so just keep that in mind. So if I want this to be a car going in the opposite direction at 15 miles per hour, you would want to make it half as long, right? Okay, well, that's close. Okay, so if I call this vector u, I say I wouldn't even have to say, but I will. The magnitude 15. Okay? So without this information, if you understood that these were in the same context, you wouldn't understand. These cars are going in the opposite directions, and this one is going half as fast as this one. You can tell from the comparison of the pictures, the relative speeds. Okay, so that's where the magnitudes are really helpful, is when you are comparing more than one thing. Okay, so remember the vector, the length of a vector, it may be 10 inches, but that doesn't mean that the units for the vector were in inches. Okay, I mean, as a silly example, I mean, if I were walking with my brother in the forest, and we're walking side by side, and we said, oh, let's make the direction we're walking is the direction of the vector, but the magnitudes are ages, right? So here I am, and then here's my brother. He's a little bit older. So the length of the vector doesn't even have to represent something logical. Here it'd be age. Okay, so you could even do that. Okay. Okay, so now that we know what a vector is, and we know what it means for two vectors to be the same, let's talk about how to add vectors. So the sum or resultant, so I'll use those terms interchangeably, of two vectors u and v denoted u plus v, right? So if we have a vector u and we have a vector v, we want to add them together. That's called the sum or the resultant, okay? It's obtained by placing the initial point of v at the terminal point of u. Now that's not the end. The sum is the vector from the initial point of view to the terminal point of v. Wow, that's a lot of words. I think it's easier to do an example. I also want you to realize that in the book they're doing a parallelogram method, but I've found from my experience teaching this course, which I've taught a million times, students can't draw parallelograms, and frankly I can't either. So that's why I teach it the way I do here. Okay, so let's do an example, and we'll follow the definition as we go. So find the resultant of the vectors u and v. Okay, so here's u. Again, you'll just have to draw this on your paper. And then v is doing something like that. Right, so draw those on your paper. Or something similar. Okay, so I want to add the two vectors together. So what does it say to do? U plus v is obtained by placing the initial point of v, at the terminal point of u. So I want to move this vector so they're head to tail. Okay, so I didn't get myself room there. Let me draw u again. So here's u. Always label your vectors so I know. So there's u. I made it too short. Okay, there's u. So I'm going to take the point here and put it at the end. Now, what does it mean for two vectors to be equal? If I want this to be v, I have to make it same length and same direction. So basically, so something like, okay, that's not bad. Okay, you see what I've done? I've just moved this vector to here and I kept it parallel. Okay, now that's not the answer, okay? It says the sum is the vector from the initial point of u to the terminal point of v. Okay, so I always think of it this way. Imagine you're walking down a path and you started here. So you started here and you walked to here, then you picked up a new path and you started here and walked to here. So what was your net result? You started here and you stopped here. So you started here and stopped here, so you went like this. So there's the vector u plus v. So the sum of two vectors is a vector. We're teaching you how to add pictures. This picture plus this picture is this picture. Now the answer is not a triangle here. The answer is this. I mean, sometimes you'll just, they'll just, there's u plus v, right? I made it same length and parallel. It's basically horizontal, the way I've drawn it. Okay, so the actual vector is this here, right? That's the actual answer. Okay, the vector going from here to here. And make sure I can see your arrows. Don't do this. You have all these arrows on top of each other and I can't see what's what. Be careful. Okay, so that's that one. The next one says it's another find the resultant, so find u plus v again. But this time u looks like this. There's u. Let me make it a little bit longer. Okay, there's u. And v is a horizontal vector going the other way. So notice, if this is a problem where you can't do a parallelogram. That's why I like the definition I have here better of addition, finding a resultant, because parallelograms, you don't do a parallelogram method with two vectors of this form. So what does the procedure say to do? You take the initial point of v and put it at the terminal point of u. Okay, so I'll just do it over here. So here's u. I'm going to take v and put it here and come back. Not long enough. So u went to here and v came back. Okay, so again, think about if you were walking. You started here and you went to here and you picked up on the other path, which is the same path going the other way, and you came to here. So where'd you start and where'd you stop? You started here and you stopped here. Now which way, ask yourself, which way am I going to draw the vector? Am I going to go from left to right or right to left? Okay, now you may be tempted to say, well, we were headed this way, so the vector goes this way, but that's not right, remember? It's you started here and stopped here, so you started here and stopped here. It doesn't matter which way you were headed, right? It's your starting point to the ending point, so it's here. So, and always label, here's u plus v. And I'll have students say, wait a minute, u plus v is shorter than u was. That doesn't make any sense. Yes, it does. We're following the definition. Think of v, we undid part of u, okay? Okay. Now, a common question that students will ask is, do you really have to be careful about the order you do these in? Right? U plus v, the definition says take the initial point of v and put it at the end of u. Is that the same as v plus u? Okay? In other words, instead of doing u and then v, what if I did v and then u? Well, let's try that on this example. So if I did v first, and here's v, now let's look at u. So if I did v first, okay, and then I did u, so I'm placing the initial point of u at the terminal point of v, so u is this way, here's u, right? Notice I started here, and I stopped here, so I started here and stopped here, and there's u plus v, and well, I made this one too long, but they're the same, okay? So it doesn't really matter which one you put at the end of which one, you're gonna get the same answer. U plus v and v plus u are the same, so just whichever way you feel like doing. In the example we did, before this, we did, u plus v, and we got that for the answer. That was u, and that was v, and that was u plus v. What if we did v first? So here's v, and then do u, which is up this way, And then where's u plus v? We started here and stopped there, so there's v plus u. And notice it's the same. That vector and that vector are the same. So it doesn't matter which order you do these in. Okay, well, let's talk about some other operations. So we know how to add two vectors. So the next definition says, if k greater than 0 is a scalar, so the word here is scalar, that just means a number, okay? In terms of vectors, they just use this to represent a number. So I'm assuming k is a scalar that's positive, so it's a positive real number. And u is a vector, okay? So we have a scalar and we have a vector. And we want to explain what is the vector ku. So what does it mean to say a number times a vector? A scalar multiple is what you call that. So a scalar multiple of u. It's a vector with the same direction as u, but the magnitude of this vector is k times the magnitude of u. Okay? So the vector ku has the same direction as u, but how do you compare the lengths? The length of this vector is k times the length of u. So ku is a vector with the same direction, but it's k times as long. That's all that really means. Okay? Now that we assumed that k was positive here. How do we handle a negative value of k? So the vector minus u, negative u, is called the opposite or negative u. It's obtained by switching the initial and terminal points of u. Right? So if this is u, what's negative u? Switch the head and the tail. So it's parallel, same length, but opposite direction. So that's what negative u would be. So that's, if this were a negative number, just do it with k where k is positive, and then the negative says switch the head and the tail. We're going to do examples. And don't worry about the zero vector. We're going to do that in the next example. Vector subtraction is defined by vector u minus vector v means u plus negative v. Now that we know what negative of a vector means, we know what it means to subtract. So to subtract two vectors, you add the negative. We already know how to add. Okay, so there's a lot of stuff going on here. Let's do some definitions. Do some examples here to practice these definitions. So out to the left on your paper, draw these vectors. So here's vector u. There's vector u. Vector v is a vertical vector heading down. There's vector v. And then w I have as a horizontal vector going to the left. Okay. So I'm going to use all three of these in these next 4 examples here. So to give yourself some room. So it says find each of the following vectors given the vectors below. So the first one says, let's find 3u. So I want the vector 3u. So 3 is the scalar here. So here's vector u. What does the vector 3u mean? 3 is positive. So it's the vector with the same direction as u, but 3 times as long. So I just have to take vector u and make it 3 times as long. Okay, that's close. Always label. And don't put arrows in the middle, right? It's one vector. Just put it at the end. It sort of makes sense, because if you thought about real numbers, what does 3x mean in real numbers? It means x plus x plus x. So you would think that 3u should be u plus u plus u, shouldn't it? But if you take vector u and you add vector u to it, you put them head to tail and add another u. So it'd be 3 times as long. So it sort of makes sense. So there's 3u. Okay, the next example says negative 2v. Okay, now how do we get the vector negative 2v? Okay, here's vector v. What would 2v look like? Okay, so 2v would be same direction but twice as long. So here's 2v. Okay, now what would negative 2v look like? Right, you just switch the head and the tail. So negative 2v looks like this. Now don't think of positive is up and negative is down. No. 2v is just same direction twice as long. So this one's going down, this one's going down. Negative 2v then is going up. Okay, that one wasn't too bad. The next one is v minus 2w. Okay, give myself some room here. So the next one I want v minus 2w. Now this is vector subtraction. The definition of vector subtraction was add the negative. Okay, so we have vector v. Okay, let me go ahead and draw vector v. So here's vector v. Right. Now what does vector minus 2w look like? Okay, it's twice as long as w, but in the opposite direction. So negative 2w is going to be twice as long going to the right. Okay, so there's v, and there's negative 2w, right, twice as long in the opposite direction. Now that's not the answer. Remember how you add vectors. I started here, I walked along the path of v, I walked along the path of minus 2w, so I started here and stopped here. That is vector v plus minus 2w or v minus 2w. And make sure you label your answers. That's the vector. Don't just draw a triangle with none of the sides labeled. And make sure I can see the arrows. I've made that one way too big, but I don't have them on top of each other. Okay? Then the third thing says v plus minus v. V plus negative v, which is v minus v. Now if you look at the definition up above, this is called the zero vector, which I would write, it's boldface, but again I'm writing vectors with a hat. So the zero vector is defined to be v plus negative v for any vector. Okay, it doesn't have to be v. But let's see what that would look like with vector v here. So vector v looks like this. There's v. And minus v looks like this. Right? So if I want to add those two vectors together, what would I do? Right? Here's v. And then you put them head to tail. So this, the initial point of negative v, goes on the terminal point of v, and I would go right back, wouldn't I? It's a horrible picture because they're on top of each other. But think about what you did. You started here, and we walked down to here, and then this point is here. Then we picked up on that one and walked back. So where did we start and where did we stop? We started here, we went down to here, and then we came back and we stopped here. So what does this vector look like? It's a single point. Right? The zero vector is just this single point right here. Because we started here and stopped there once we put that one on top. So the zero vector is a point. It's okay. So what's the magnitude of this vector? Zero. There's no magnitude. And what's the direction? There is no direction. How do you determine the direction of something? It's where something was. It's where something is compared to where it was. Right? That's the direction. So if you're here and you don't move, then there's no direction. Okay? And it makes sense to call that the zero vector. Because what if I did vector w plus the zero vector? Right? What do you get? Okay, here's vector w, and put the vector the zero vector at the end, which is a point. So what'd you do? You started here, you walked to here, and then you stayed here. Notice what you got. You started here and stopped here. You got vector w again. So it makes sense to call it zero because you think of in the real numbers anything plus zero is itself. So any vector plus a zero vector is itself. So it makes sense to call it the zero vector. Right, so just remember the zero vector is a point, a single point. Okay, so now we're going to shift gears again. We have two applications to do here. Okay, the first one says two forces of 37.8 pounds and 53.7 pounds act at a point in the plane. Now I have to tell you what that means. So imagine, right, there's, say, a desk or something, and you're attaching two ropes to it. So one is pulling out here with a force of 37.8 pounds, and another one is pulling down here, say, I'm not trying to get this to scale, of 53.7 pounds. So this is what they mean. Two forces act at a point in the plane. Now they say in the plane because they don't want somebody pulling like this and then somebody's up above pulling like this. Okay, so they're in the same plane. The two ropes are in the same plane. Okay, it says the angle between the forces is 68.5 degrees. So this angle right here is 68.5 degrees. Okay, that's what they told us. Find the magnitude of the resultant force. Okay, now where's the resultant? Be careful. The resultant is not the vector from here to here. Do you understand why? Because the way I explained to do this, you don't have the vectors with the initial points locked together. They have to be head to tail. So you don't add these vectors by drawing a line like that. No, I know you want to make a triangle, but that's not what it's going to be, right? So again, in the book, they're drawing a parallel. They're putting them tail to tail, or head to head, whichever. So they're putting them like this and then making a parallelogram. So if you look at the pictures in the book, they're drawing parallelograms. I'm not going to do it that way, right? So to add these two vectors, I need to put them head to tail, okay, head to tail. So I'm going to move this vector to here, so make it parallel and same length. Well, that's close, right? So this is 53.7 pounds, right? So I've just moved this vector. Yeah, I could have moved this one to here. It doesn't matter, right? So this one I moved to here. I started here and went to here, then picked up from here to here. So I started here and went to here. So this right here, this is the resultant, right? The sum of two vectors. This vector plus this vector is that vector. There is a resultant, right? And that's what we're trying to find the length of, right? Find the magnitude of the resultant force. I'll just call that X thing. And now you have to be careful here. I mean, if I finish this off, I would have a parallelogram, right? Diagonals of parallelograms do not necessarily bisect an angle. So I can't just take half of 68.5 degrees and put half there and half there. It doesn't work. It doesn't work that way, necessarily, okay? So you can't just do that. So if I want to, notice I know this, I know the length of that side, I know the length of that side, I'm looking for this, and I have the angle I know is from here to here. Okay, so we need to come up with a fact to get something in the triangle here, right? Part of this angle is in the triangle, but not the whole thing. Now let me see if I can do that from memory. Let me draw this picture again, so just so I don't mess that one up. Okay, let me call this angle alpha, and let me call this angle beta. So I know alpha plus beta is just 68.5, right? And let me call the angle up here gamma. Okay. Oh, okay. Now what do we have here? This vector and this vector are parallel, right? Because these vectors are equal, so they're parallel. And notice here I have a transversal, right? If you extend that, I have a transversal. So if you go back, think about the picture we had before, I drew those lines horizontally, the parallel lines cut by transversal. Notice these angles are alternate interior angles, this one and this one, so that's beta, isn't it? Right? Two parallel lines cut by transversal alternate interior angles are equal. Well, if that angle's beta, what do you know about alpha plus beta plus gamma? All three of these angles are in this triangle, so they sum to 180 degrees, don't they? So what's gamma? Angle gamma is 180 minus alpha plus beta, isn't it? Right? Subtract alpha plus beta from both sides, that's what you get. So I don't know, notice in this problem, I don't know alpha, I don't know beta, but I do know their sum. So if I say 180 degrees minus the angle between the vectors, that'll give me the angle up here, gamma, that I've called gamma. Again, I just made up these letters. Okay? Okay, so that's a fact you should just remember, so you don't have to figure this out every time one of these problems comes up. So what do you know about the angle between the two vectors here and the angle up here? If you draw the picture the same way I did, they're supplementary. So if you subtract 68.5 from 180, you get 111.5. Is that right? 179.8, yeah. Okay, so just the angle they give you here, subtract from 180, and you'll get the angle up here. And what's different? Why is that angle much better than the one here? This angle's completely inside this triangle, and this one's not, only part of it is. Okay, so that's a fact you just need to remember to do these forces acting at a point problem. Okay, now, do we have enough information in the triangle here to find x? Well, could you use law of sines to find this problem? Well, I'm looking for side x, and I have the angle that goes with it, but I don't have a pair, right? You can't say 53.7 and 68.5 because you'd have to use that angle, which I don't know. So you can't use law of sines. Now, can you use law of cosines? To find something with the law of cosines, you either need all three sides to find an angle, or you need two sides and the angle in between to find the other side. And notice I have two sides and the angle, two sides and the angle in between. Okay, so I can do that. So if you need to call these A, B, and C, that's fine, but remember, if I'm trying to find side x, start with side x squared is the other two sides squared, 37.8 squared plus 53.7 squared minus 2 times those two sides times cosine of the angle in between, which is 111.5 degrees. 37.8 squared, 53.7 squared, 2 times those two sides cosine of the angle in between. Okay, so we just have to punch that in. That shouldn't be that hard, I say. So 37.8 squared, you should punch it into 53.7 squared minus 2 times 37.8 times 53.7 times cosine of 111.5. And I'm getting, this is x squared, 5800.42236. So x here, if I take the square root, I'm getting 76.16 to 2 places, and that's pounds. Okay? Now does that make sense? You've got somebody pulling with almost 40 pounds of force and somebody pulling with almost 54 pounds of force, but the resultant force is only 76 pounds. These two people are putting forth a lot of effort pulling this desk, but they're only really pulling with 76 pounds of force. Why is that? Well, think of it this way. Right? So imagine I had a desk right here with a rope attached, and I was standing to the side, back here, and the desk is up here, and I'm pulling like this. Now, which way is the desk? If I was pulling by myself, which way would the desk go? Well, if I pull like this, it's going to come this way, forward, but it's also going to come to the side towards me, won't it? Right? If the desk is over there, ahead of me, and I start pulling like this, the desk is going to come forward, but it's also going to come to the side. Now imagine the person over here pulling with 53.7 pounds. They're over here on the other side, so the desk is out here, and they're pulling this way. Well, the desk is going to come forward for them, but then it's going to want to go back to them that way. So the vertical force, having the desk come forward for both of them is great, but what's the problem? One person is pulling, and the desk is wanting to come this way. The other person over here is pulling, the desk is wanting to go that way. So those forces are canceling each other out, right? They're pulling against each other in that regard. But together, they're still pulling the desk forward. So that's what this is saying. So this is taking into account the when the desk is wanting to go forward in this way, right? The desk wants to go like this, but the desk wants to go like that. This is the canceling out of the two horizontals. Okay? So this is the same as one person pulling dead on. So instead of being to the side, if one person was pulling dead on with 76.16 pounds of force, that would be the same effort that these two were doing it this way, with that angle in between. Okay, let's do another one. And I think drawing the picture helps. Now this one won't take us as long as setting up because we know how it works. Two forces of 128 pounds and 253 pounds act at a point, okay? So we know what that means. So 128 pounds and 253 pounds. Again, I'm not trying to get this to scale. This one's longer, so fine. 253 pounds. 128 and 253 act at a point. The resultant force is 320 pounds. Okay, so if I add these two together, so if I move this to here, right, if you don't like something you've written down, erase it, please. Okay, the resultant is here. And they told me the length, the magnitude of the resultant is 320 pounds. So this is 253, and this is 320. Now this one says find the angle between the forces, meaning here. Now I hope you realize this is the previous problem in reverse. In the previous problem, they gave us the angle between the forces. They said find the resultant. Here we have the resultant, and we want to find the angle. Well, what was the procedure in the previous problem? We had the angle between the forces. We found the angle up here, and then we used the angle up here to find the side. So let's go backwards. Use this side and the others to find the angle up here, and then subtract the angle up here from 180, and you'll have the angle between the forces. Okay, so I'm just going to call this angle up here gamma, just because I called it that before. You can call it whatever you want. So I want to find angle gamma. Well, to find an angle with the law of cosines, again, you can't use law of sines here. You start with the side opposite. So 320 squared is 128 squared plus 253 squared minus 2 times 128 times 253 cosine. Again, there is a formula in the section 7.3 where they actually solve for cosine gamma, and you don't have to do the extra steps I'm going to do here, but I find it easier just to do it this way. I don't have to memorize another formula. So 320 squared, that's 102, 400. Again, I'm going to add these two numbers together. 128 squared plus 253 squared is 80393 minus 2 times 128 times 253 is 64,760. And again, you should be punching these in. Make sure you get the same thing. Now remember, you cannot combine these numbers because this is the product. It's order of operations is products before differences. So we have to subtract the 80 from both sides. So that's 22007 negative 64768 cosine gamma. So cosine gamma is that over that, 22007 over negative 64768. So there's cosine. That's the cosine of gamma. How do you get gamma? Cosine of gamma is a number. So gamma is cosine inverse of the number. So if I take cosine inverse of 22007 divided by negative 64768, I get about 109.86 degrees if you round the two places. Is that our answer? No, that's not our answer. It didn't say find the gamma. It said find the angle between the forces. So the angle between the forces is 180 minus the gamma, which is what, 70.14 degrees. Subtract that from 180, that will get you the boldface angle. Okay, so it's just a previous problem in reverse. Okay, so then the last type of problem here is what I call the car on the hills problem. So it's just a matter of telling you how to set these up. Find the force required to keep a 3,000-pound car parked on a hill that makes an angle of 15 degrees with the horizontal. Okay, so imagine I have, here's level ground, say, here's a hill. And the hill makes an angle of 15 degrees with the horizontal. Okay, 15 degrees is there. And I have a car on the hill. I'm just going to put a box because, as you know by now, I cannot draw. So this is representing my car. Now, the car weighs 3,000 pounds. Now, how does, weight is a function of gravity. How does the gravity vector work, okay? Gravity is a force from the earth, pulling you down to the earth. So the gravity vector is represented with a vertical vector, and it's 3,000 pounds. Okay. Now, what force is needed to keep this car from sliding down the hill? Well, you can either think of as a force, holding it, pushing on it so it doesn't slide, or a force pulling on it to keep from either way. So I'm just going to imagine the force is here. Okay, so this is the force. And again, we're ignoring friction and all this kind of stuff, I suppose. Okay, so well, I'm just gonna. I assume they have the physics explanation in the book. I'm just gonna cut to the chase here. So if I move the force vector down here, right, it's parallel to that. That makes a right triangle here, where the right angle's here. So the weight, the gravity vector is the hypotenuse. Okay, so this is a right triangle. The right angle's here. And this is the force vector down here, right? So this is the force here. Again, I'm just kind of doing some hand waving. This is one of the few times I do some hand waving. Okay, now, so this is the triangle we're going to be working with. So we're looking for the magnitude of the force vector, and we know this side. But what's the issue in this new triangle I've drawn? I don't know any of the angles. Well, besides the right angle. And that's not going to help us, right? Okay, let me call this magnitude x. Okay, so that's the force vector down here. So if you move the force vector down here, make it parallel, you'll get a right triangle here. The right angle's over here. The gravity vector is the weight is your hypotenuse. Okay, now how did this go? So again, we have to derive a fact, and then we'll just use it from here on out. Okay, right. Okay, let me draw the picture over here, so I don't mess this one up. Okay, so if you imagine this side being extended, this one here, where the force vector is. Notice this is parallel to the hill, right? When you're pulling the force here, it's parallel to the hill. So I have here two parallel lines cut by a transversal, this transversal here. So I'm not really using this side at all to argue here, okay? So what would have to be true, and I'm not really using this one either, alternate interior angles would be the same. So this angle and this angle would be the same, okay? Two parallel lines cut by a transversal, alternate interior angles are the same. Well, this angle's 15, right? That's a right angle. So how could you figure out this angle? Well, it's 90 minus 15, so that's 75 degrees. But this angle down here would be 75 degrees. And if I add my picture back, well, that's bad. That's a right triangle, which makes this one 15 degrees, right? So this triangle and this triangle here, they're similar triangles. Okay. So this angle's 15, this one's 75, which makes this one 75, which makes this one 15. So this angle right here is also 15. So that's the fact you should just remember. The angle that the hill makes with the horizontal is equal to the angle in the triangle you've drawn here. Okay, so I would just memorize that and you don't have to figure it out. Okay, so now let's look at our picture. This is a right triangle. Don't use law of sines or law of cosines on a right triangle. Hey, pardon the pun, you're going to use a cannon to kill the fly. Okay, so I'm just going to go back to right triangle trig stuff. So what's the procedure? Choose an acute angle and two of the sides. Make sure you know two of the three things, which I do. Now, which trig function relates to this angle to these two sides? Okay, so I have the opposite and I have the hypotenuse. Remember, the gravity vector is always the hypotenuse. That's sine. So sine of 15 degrees is the opposite x over the hypotenuse 3000. Right, so how do we solve for x? I just need to get rid of the 3000, multiply both sides by 3000, and there's your x. So we just have to punch that in. I got x is 776.46 if you go to two places pound. So to keep that 3,000 pound car from sliding down the hill, you need almost 800 pounds of force to do it. 15 degrees is pretty steep. You think, geez, that's kind of high, you know, compared to that. It's about a fourth of the weight of the car you need to keep from sliding. A 15 degree grade isn't pretty steep. Okay, let's do one more. So again, this one won't take as long because we know how to set it up. It says a force of 500 pounds is required to pull a boat up a ramp inclined at 18 degrees with the horizontal. How much does the boat weigh? Okay, so we have a ramp. And the ramp is inclined at 18 degrees with the horizontal. I have a boat. I'm not going to try to draw a boat. I can draw a box. That's my boat. It takes 500 pounds of force to pull it. Okay, so 500 pounds of force is what that is. And we want to know how much the boat weighs. So here we're looking for the gravity vector here. I'll call the magnitude x. Okay. Now if you think about these cars on the hills problem, what are they going to do? There's three things involved. The angle of inclination here, the force, and the weight. They're going to give you two of them and ask for the third. So they could give you, notice here they gave us the angle and the force, they want the weight. On the last one they gave us the angle and the weight and they wanted the force. Or they could give you the force and the weight and ask for the angle. I mean, there's only three variations here, but the picture's the same. So if I put the force vector down here, that's 500. That will make a right triangle where the right angle's over there. The gravity vector is the hypotenuse. And we learned from the previous problem, the angle here is the same as the angle here, so that's 18 degrees. Okay, so choose the acute angle on two sides. You're always going to choose those. And notice it's opposite hypotenuse, that's sine. So sine of 18 degrees is 500 over x. Sine is opposite over hypotenuse. So here the variable's in the denominator. We need to get it out of the denominator. Let's multiply both sides by x. And then divide both sides by sine of 18. And that should be our weight. So I got 18.03 pounds. Notice in the previous problem it was about a fourth of the weight was the force. Notice here it's you know a little less than a third. It got worse. Well, why is that? Well, the angle's even more. It's 18 degrees. Right? That's even steeper than in the previous problem. Okay, so there's our two application problems in this section.